Low temperature differential Stirling cycle analysis. The beginning of this year, I had planned on building a Stirling cycle engine, and you'll hear me call it a gamma type as well. Low temperature differential and gamma type, they're one and the same. I intended on building one with some modifications that I designed for, and we'll talk about the design process in a little bit. But it was just simply too much time once I actually analyzed everything, figured it out. The whole point on me making a new engine would be to optimize one that I already have, to make it better than what it is. And in order to do that, I'd have to test it. I realized really quickly that this is not a simple engine to test. Very, very low power. You can't do what I intended on doing initially, a simple prony brake, friction prony brake. Just put a friction pad on it, allow the engine to spin still, and have a cantilever beam on one side with a scale. And then you know the force, you know the distance from the center, and you know the RPM, so you have power. I couldn't do that in this application because, as you can see, with all gamma types, at least with this configuration, connecting rods are on either side for both the displacer piston, the larger piston on the bottom, we'll get to that, and the power piston. That's the basics of the start. I want to, for people who aren't really familiar with Stirling cycle engines, I kind of want to go through the phases a little bit. And I think the easiest way to understand it is with Carnot cycles efficiency. So if you have a graph here, you guys can see that? Okay. So if you have a graph, I'm going to grab my cheat sheet here. Got some pressure here. We have a volume here. So if this is the first cycle, the volume is going to stay the same, the pressure is going to increase because the cylinder is heating up, the temperature is driving the pressure change, okay? Now, in between 2 and 3, as it says there, now we have the power piston is now, in the first phase, the power piston, the smaller piston, is standing still because it's on the lower end of the cycle, so lower end of the connecting rod, and it's staying still, keeping the volume relatively constant. Between 2 and 3, both of them are moving. They're coming together. We're getting a little bit of a pressure differential, and then what really the guts and glory right here between 3 and 4. Now we're ready for the next cycle because now the displacer piston is staying still. The power piston's coming in. We're creating a small vacuum, and now the temperature has dropped as low as it's going to get. And now you're ready for the new cycle, and all of this is happening in one rotation. We're coming back, and now we're ready for the power stroke again. This was huge in trying to establish the analysis for this engine because this isn't what's happening. This is what's happening ideally, but as we know as engineers, people who talk to engineers, ideal is not real. So what's really going on is we have this elliptical fashion here. And so when you're trying to design for that, the only phase that you're going to get any power out of is phase 1 to 2. So I needed to ensure that I could overcome the friction coefficient, not with my power phase. That's pretty easy. What I need to make sure is that the moment, that flywheel effect, literally the flywheel effect of the engine would carry it past that friction coefficient. And I didn't realize this until just a few months ago that was such an extreme deal. I went through 5 different design configurations before I finally found one that would work. And I'm literally using decoration ribbon. The intention was when I first did my predictions, I wanted to make half a horsepower or a quarter horsepower and about 500 RPM. I say about, that's really hard to say as an engineer, but because of the lack of information about these engines, I kind of had to ballpark it in the beginning. So I designed it for that. I designed for, actually I designed it for a quarter horsepower at 500 RPM, and I couldn't get my gauge material to move with, and still allow the engine to overcome the friction coefficient. Okay, so now it's back to the drawing board. Now what do I do? So we'll move on to the next tab here. Maybe manufacturing. Okay, so there's the build. There's the fancy stuff. Okay, fail. So this is one of my fails here, and I'll show you the video in a second. But my first problem was, when I first designed it, I was just assuming way too much power. Like I said, there's not much information out there. The only people I've found that published anything about this is NASA, and they found out later they put $500,000 into this engine. Obviously way more efficient than mine. They were using pressurized helium. They had a truly fixed volume and a charge inside the cylinder. They were running about 4 bar, and they were still only getting a few watts. So a few watts at the temperature range that I'm looking for. So like I said, it was back to the drawing board, went through several different configurations. Roger Beardsley was kindly enough to help me out finding a configuration that would work. And what it came down to was making this flywheel making the moment of the flywheel, giving that effect of the flywheel what it just deserves. So this is here's the failure here. Oh, there's the cylinder movement. Yeah, fancy stuff. Like I said, this is preliminary testing. This is just to see what's going to work and what isn't. See, now what's nice is I got deflection this time. I went to a 25,000 thick aluminum. I got deflection. We're making progress. Stuff's happening. What I ended up going to next was, again, to allow that flywheel effect to do its motion, I just simply made the moment smaller. I brought it in closer to the center of axis, and I finally got some deflection that would work. You see 2 strain gauges here, both these cantilever beam strain gauges that I calibrated. The intention was to use 2 strain gauges, figure out my friction coefficient, and then have the unloading strain gauge approach 0 but never reach 0. That proved really, really difficult and kind of arbitrary. It ended up not actually proving anything to the effect of the engine that was useful. I went back down to 1 strain gauge and finally got some results where the engine, you'll probably be able to see it, maybe, hopefully, not enough tension on it, but as the engine rotates, it puts enough load on that strain gauge to where it'll deflect enough and I get a measurable amount. I could not overcome, even though I intended to make 500 RPM, it's a little too ambitious. I could not overcome friction coefficient the viscous friction of the engine over 200 RPM without a load. My actual results came in around 50 to 60 RPM and within the milliwatts, really, really, really small values. I'll go into the testing results here, maybe. Okay, yeah, see, maximum power that we got out of this thing, at 66 RPM, we got 15.8 milliwatts. Not an easy power rating to really find. I'll pull up this graph. This actually came out pretty interesting. Like I said, I could not overcome my viscous friction, so that was the limit. For my working fluid, I'm just using standard air, simply because I couldn't charge the cylinder. I didn't have a true fixed volume. There are leaks, there are problems. This is a demonstration engine, not a true testing engine. And mainly because of money, I couldn't really get a better one. So I got my max power at the maximum temperature that I tried, which is not surprising. However, it seemed that the more and more I went up, the closer I got to 200, but again, could never exceed. When I approached what I thought would be the max, according to MatWeb, most of you are probably familiar with MatWeb, I decided to go to 210 degrees centigrade was my limit. That's about this melting point of styrofoam, which is what the displacer piston is made out of. And I decided to stay below that. I stayed at 180 degrees centigrade, and I think that the cylinder was just tight enough that I built some steam and warped the cylinder, and I ended up ultimately melting my engine, halting the test. But as you can see, I'll pull up a bigger picture. These are my results. I'll make this kind of quick, I'm running out of time. But there's a clear trend between the delta T and the actual power output. Again, these are in milliwatts, this is very, very low power, but there's still clearly a trend. And up here, this is where the engine failed before I knew it. Thank you. If you guys want to know any more information, again, I'm running out of time. We'll go over one more thing here. There's my website there if you want to write it down or not. It's up to you. So this is really just a model of what the viscous friction was doing for me. Within experimental uncertainty, this was relatively linear. I think maybe if I could have gotten higher delta T, I could have got a little bit over 200, but it seemed to plateau. It rose close to 200 pretty quickly and wouldn't go past that. I budgeted $105 for this project, if I remember correctly. $105, and I got, it took me $165, and that's not really including all of the research that I did for it. This was mostly a testing and experimenting, research and development kind of project, more so than manufacturing. My cost was just under budget, but really close, and my maximum efficiency was less than 1% when I predicted, oh, I didn't put it up there, but I predicted 2% with standard air, and 5 for helium. And I guess I'm out of time. Any questions?